So first of all, thank you very much for inviting me to the BTS organizers. So I knew about BTS since a long time, since the very beginning. I remember when we were at the SOSI competitions, I was talking with Nicola and he told me, Francesco, I think you should go to BTS next time. And I followed that advice just a few years later. It's also great that Fausto was presenting me because he's one of the first people I've met in the marine robotics community about 12 years, 13 years ago from now. And actually in this BTS, we have 4 people that were a student in a European project in 2007, 2008, when we were all young and full of dreams about the future. And then it's so nice that after so many years, we are here, and some of you are actually from that group of projects, from that project that was supporting student activities, exchanges, and so on. So my presentation comes after a few days of intensive, high-quality activities and lectures, and I will talk a bit about intelligent localization and why we need localization and what are various approaches that we have been working on in the various places I've been working on, from Heriot-Watt University, and then when I was in MIT, and now in Jacobs University. So we have seen in the past few days quite a few interesting stuff. So for example, we had a presentation on an intelligent tablet to see about archaeology. But then, if we see something interesting and we have an intelligent tablet, of course, we need to know where we are. We need to know where this interesting stuff is located. So now this is a diver, but if we move from a diver into an AUV that moves around, it finds some interesting stuff, then we need to know where the interesting stuff is. It's not enough to say, well, here is a treasure, if we don't know where it is. We've also seen a very cool presentation, well, not from this system, but it was a presentation on ROV docking, AUV docking. And also for this kind of activities, we need to have some sensors, some information, some processing, some intelligence that tells us where the vehicle is with respect to the docking station, and so on. So localization is a really key area for reliable navigation. So if we have any tasks that we need to accomplish, we need to know where the vehicle is. The vehicle needs to know where it is. And it can be essentially divided in 2 main categories. So it's a global positioning. That is a kind of a GPS in case we are on land. So we know our absolute coordinates. Then of course GPS doesn't work in the water, underwater. Or it can be relative. So we want to know our position relative to the specific environment because we want to do some inspection, we want to do some manipulation, and so on. And it's a real enabling factor for real-world application. So for example, for inspection, so MCM, mine countermeasure missions, are one of the main applications in defense of autonomous underwater vehicles. Archaeology, so we use this very similar software for both missions. In both cases, we are looking for something in the water. Either it's some archaeology stuff, either it's a potential mine and threat, or for intervention. So if you want to go to a panel and manipulate, for example, turn a valve and so on, then we need to know the relative location of the vehicle with respect to the panel. So when we talk about localization, the main thing that we all think about in the marine robotics is acoustic localization, for example, LBL system or SBL, USBL. So they're all acoustic systems that we put into the water somehow, and they help us to understand our position. So for example, in this case, we have a diver, but it would be the same with an AUV. That it gets some information from the transponders, and then it gets calculate its own location. And we have seen also great demo from companies here that they have excellent systems with LBL, USBL, and so on. Now, the drawback of this is that we can't always use that system. And it's not something that we humans would do all the time. So if we think about when we are working in a city and we want to know where we are, of course, we can use Google Maps and check our GPS position and fix, which would be kind of the similar way than an LBL system in the water. But in most cases, we would just look around with our eyes, and then we are processing some information through our brain to understand where we are. And we are not only looking at the fix from our mobile system. That has the advantage that if we can have an AUV that can localize itself without external aids, it simplifies operation, and we can operate also in places where it's not feasible to put these acoustic aids. Now, the problem is, I said, well, if I am in the city, I can see things with my eyes, and then I can process, and I can try to recognize where I am. Like, for example, here I'm walking around, I see a pool, and then I say, okay, maybe I'm in front of the hotel. Now, in the water, we don't always have information to see, so it depends on where we are. So before going to the details of some of the activities that we've been doing, we need to set the scene and essentially in which conditions we are operating. So we are operating in conditions where we can see something with our sensors. We are using sonars, but we could also use cameras and other kind of sensors. But we are not tackling the problem of localization, for example, in mid-water in the water column. So we are tackling the problem of localization where we can see something around. So a typical example is in front of a panel, or this is an abandoned marina in Catalonia, that if the vehicle swims around here, then we can see the wall. So in all harbor conditions, for example, whenever we see something, then we can use the techniques that I'm going to present. And then we have been working based on particle filters. So particle filters is a very nice system to estimate localization. And it has the advantage that you don't have to know your own location at the beginning. How does it work? Okay, I'm not going to give a lecture on particle filter, but just for some people that they might not know, just a couple of information. So it works like a Monte Carlo localization, while Monte Carlo, because all possible numbers in this system represents, let's say, a possible state of the vehicle. And we don't know that, and we need to try to identify that. So if we move towards a practical example, if we want to find the location of a robot in a room like this, each of these points represent a possible location of the robot in the room. We also know the room, we know where we are, we know the environment, and we know all the possible states that we are starting with. So from each of these states, we can simulate the measurement, and then we can compare with the original measure from our sensors. And then based on the similarity of these two, we can say, well, it's very highly likely that the location of the robot can be in this area, or it can be in this other area, and so on. So if we apply this algorithm for the next step, for example, then we can see that we already trimmed a lot the space, and the possible location of the robots are actually here, here, or on the other side, on the bottom side, we can, no, okay, fine, can't point. And here is a famous GIF that shows how the particle filter localization works. So at the beginning, you don't know where you are, so you can spread particles all over the place. The robot is moving, then you can get your sensor data. You compare with the simulated sensor data from each particle, and then you can arrive, now you arrive to two hypotheses, and then when the robot enters into this room, the hypothesis down disappears, and the robot has successfully localized itself. So the first approach that was a long time ago was to use this well-known technique in mobile robotics in indoor areas in the water. So it was a geometric approach, so we were considering geometric localization and the distances and geometric information about the environment. We were doing data processing on the sonar. So we've done some simulation data, and here is the same environment that I showed in the picture before. So this is an abandoned marina. The vehicle was moving around, and only working with dead reckoning, the vehicle would be up here, so not in the water anymore, but then correcting the information, correcting the location with the technique, we arrive to a very stable, very good localization inside the canal. And then we were happy, but then as soon as we get some results, we always say, well, what is the next step to do? So what is the problem of this? So we, as scientists, we're never satisfied, and we say, yes, that's good. And we started to think about this. And the big problem that we realized when we were discussing this technique is that it's mainly a passive technique. Now, passive technique can mean various different things in different communities. So for the purpose of our work, passive means that we are just processing the data in a passive way. So there is no robot control or no intelligent decision making in the loop. So in this case, there is no loop inside to tell the robot where to go. So if we consider, for example, this situation where we had the room, at some point we had two big clusters of particles, but then there was no decision for the robot to say, okay, I'm going to enter into the room in order to drop the uncertainty. So this robot was probably operated manually or autonomous, but it was operated manually. But in this case, there was no decision to say, okay, I'm entering into the room because I want to know my location. And one of the big problems, if you don't have any control in the loop, is that we might move randomly all around the place, but we might not do the things we need to do in order to localize ourselves. And this was also coming from talks with industry, especially in the oil and gas, thinking about persistent autonomy, long-term deployment. You have vehicles that they would, in the ideal case, they stay there for a long time, and they move from one site to another site, and the error in the transit can be larger than the distance between two very similar structures. So if you only use particle filters, say, in a passive way, you arrive to the second site, you see some structure, but you don't know if you are in front of structure A or if you are in front of structure B, because these are very similar structures, and the error in navigation can be high. So we started to think about adding some intelligence when we can cluster the particles. So whenever we arrive to high-peaks hypothesis of the vehicle location, we were saying, well, then it's probably the time to start and take control and say, well, if I really want to localize myself before doing some actions, because you don't want to turn the wrong valve on the wrong panel, then say, okay, now there are some peaks, so I don't know if I am in front of structure A or B or C, they're all similar. What can I do in order to understand where I am, instead of just moving randomly? So this is what we call active localization. I know that in other communities, active and passive refers to the acoustic, if it's active acoustically or passive acoustically. But in this case, we are very much interested in active, meaning a control in the loop on decision making. So we have several different hypotheses. So what we can do, we can build, we start with a tree-style trajectory, but then we extended it in a general set of actions from each of these possible hypotheses. So in this case, in a simplified case to show, so we have 4 possible actions that we can do. So we can move forward, backward, on the right or on the left. And then from each of them, of course, we can do the same. Now, the problem of this is that trees are computationally not very efficient. So we started to trim, so we can cut the basic loops. So if I'm going forward, I'm not going backward in the next one. And then I'm going to cut all the different loops, all the square loops and all the other loops, because I want to go from the different hypotheses to locations that are different from what I've already visited. Now the question is, okay, I'm going to do this tree-style trajectory from all the possible clusters, and the idea is, well, how can I evaluate which cluster is the best? So from each cluster, we can, from each node of the tree, we can simulate the measure. We can simulate the sensor because we know the map. We are working on a localization problem. And what we want to do is to execute the set of actions or the set of trajectory which would give the most of differences in the expected simulated measurements. Why that? So let's think about if I am in front of this row and I can see a chair, I can see some people. If I am in front of this other row, I can see as well chairs and some people. Now, what would be best to localize myself? To go forward or, for example, to turn on the left? So if I go forward from these two possible locations, I'm going to see very much the same thing. But if I turn from this position, I see the wall much closer than if I turn from that position. So the two possible measurements would be very different. So that is what we are seeking, is the difference in the expected of the measurements. Then we have done some interesting tests. And we started with a maze, because we thought that a maze is the delocalization problem where you need to find your way, understanding where you are. Then we moved into real vehicles. So this one was relatively simple. So we had one divisor in the pool. And then we can see that in these 4 pictures, we have the map of the pool with the division in the middle. And all the points are the possible location given by particle filters. So we can see we have 2 big clusters at the beginning, and then we say, okay, we have 2 clusters, so we can perform some active localization in order to kill one of the 2 clusters. And then at the end we do that. This one is a slightly bigger experiment that we've done in the wave tank in Edinburgh. We can't see a lot, but we have a very symmetric environment here. The vehicle is in front of one of the structure, but it can be also in front of the other one. It doesn't know where it is, so it needs to think about and say, okay, what are the actions I have to do in order to localize myself? So it's trying to put some embedded intelligence and decision-making in the localization process, so that it's not only passively processing the data, but it's actively deciding what to do. Then for a while, we moved away a bit from the localization problem, and we were working on persistent autonomy, long-term autonomy, and what are the key enabling factors for persistent autonomy. And we devised a kind of an ontological world model about the vehicle system, the environment surrounding the vehicle, all the relations between components, capabilities, actions, and so on. I go into that because the things that we have developed in active localization, we have used that now in order to understand the environment in an inverse of the problem. So if we look about, so in this case, we have 3 main subsystems in our vehicle cognition system. So we have the first subsystem A, which is gathering data from the sensors, then processing this data and putting them somehow in our cognitive knowledge base. Then we have a subsystem which is about the internal part of the vehicle that links capability, actions, and there is some fault management actions, fault management framework inside. And then we have a subsystem about the planning system. Now, if we think about a planning mission that, for example, we have to inspect all these structures that you can find in this area, first, you need to recognize the structures, and then you signal to the planner, hey, I have recognized this structure. Now, sometimes it's that we can't only use one image, for example, one image from the sonar or from the camera to recognize things, because if we see something like this, then I don't know which kind of shape it is. And that is the same, now this is an example about geometric shapes, because it's easy to understand. But also we can have several different similar structures in the water that we know, but only see one view wouldn't be enough to understand and to say to the knowledge base, yes, this is this specific structure, and then the planner needs to inspect them. So what we did was essentially reversing the problem of active localization. So in this case, we know the location of the robots, at least in a relative way, but we don't know the environment, but we have a finite set of possible environments, of possible shapes, of possible objects. While in the previous case, I didn't know the the location, I had a finite sets of possible locations, but I knew the environment. So it's essentially it's exactly the same problem, but it just flipped around. And we did some work on actions to understand what are the best set of actions to recognize the structure that you have in front of you. And then we continue to developing this system about semantic information. So that means it's very popular again in indoor robotics. There is a lot of work done in semantic work, semantic recognition, semantic localization. Not much in the water. One reason is that, of course, the environment, if the water is much sparse, in the water column you don't have much to say. But there are places where you can actually put a lot of information in. And then we were discussing the idea, well, if we are already filling our knowledge base with information about the environment, which are more high-level information on concepts rather than only geometry values, can we use this information to localize ourselves? And that goes into the kind of how to use semantic information for localization. Now, again, we need to make a quick break on terms and words, because different community means different things with the same word. So what we are looking on is not really semantic localization, but more semantic aided localization. So semantic localization in most of the indoor robotics community means that you understand more or less in which area of the house you are, for example. So if you can see a bed and a table, and you say, well, maybe that is a bedroom. If you see a table and you see chairs and you see a sofa, say, okay, maybe I am in a living room, and so on. On the other hand, we don't have this kind of environmental segmentation in the water, so we are not interested into that level of semantic localization. But we want to still get the geometric information about where the vehicle is, but we want to be aided by the semantic concepts which are around. So if I can see a panel, if I can see a valve, if I can see different structures around, that are not only geometry, they're not only point clouds, but they have specific meaning and specific concepts. So we are interested in geometric information, and we want to use the semantic information about the environment to localize ourselves. So what we did was to change our original particle filter algorithm that works very well for geometric information to make it working for semantic information. So the general algorithm stay pretty much the same, but the main important change is in the importance weighting. So that is essentially the step of the algorithm where we can assess how reliable is a possible hypothesis, how this hypothesis is close to the real state estimation. So if we remember the picture about particle filters, we have several different hypotheses, and then we have to evaluate how each hypothesis is correspondent, is likely to be very close to the original one. If we have geometric information, it's relatively easy because we can have an array of distances, we can calculate well-known calculations. Now, if we have semantic information, it's a bit different because you have much sparse more information. So you don't have point clouds, but you have, for example, just 3 or 4 concepts around. So we need to define a set of information in order to weight these particles, which are both based on the number of objects, the number of concepts I can see in the 2 scenes, and at the same time, the geometric displacement of these objects in the scene. So it's much more complicated to estimate the similarity between 2 scenes than estimate the similarity between 2 geometric distance arrays. So we've done some preliminary work on that. And the interesting results that we got is that the error using semantic aided localization compared to geometric localization wasn't changing much. So in our setup, we actually got a slightly decrease of the error, but that was not, I would say, not something that it would be very important to say. So it was just a slight decrease. But the main important results is the improvement in performances, about 1 to 6. Because when you are processing a geometric information, you have so many different points, and you are processing all this information. While if you are processing only some concepts, you have much more sparse information. So in our case, we got a reduction of computational complexity in time that we needed about 1 to 6 with the semantic aided versus the geometric. Now, to be fully honest, actually, this number doesn't include the building of the semantic map. So if we also need to consider the time that we need, the resources that we need to build the semantic map, then there might be a trade-off and it might not be very valuable. On the other hand, the building of this semantic map is very much a need for a lot of applications. So it's very much a need for the planning system to replan dynamically when there is a change in the environment that needs to do something. So essentially, we can still claim that we got a big improvement of performances, considering that the semantic map is kind of given because we need that for so many different applications. So in the future, we want to expand this work, putting the active part in it, so doing active semantic-aided localization in the same way that we did for the geometric part. And we want to work a bit more with probabilistic maps, adding more uncertainty, and not really adding more uncertainty, but just addressing the uncertainty that is in the system. So as soon as we are in the water, we don't have to add uncertainty. There is a lot of uncertainty also in the map building, in the semantic map that we are building, and how we can address also the probabilistic maps inside our localization system. Now, my talk is on localization in marine robotics, and I've only talked at the moment about underwater robotics. But intentionally, I didn't call it in autonomous underwater vehicle, I called it marine robotics, because we did some work also on surface vessels. And here I'm going to give the word to my colleague, Dr. Krupinski, that he will continue with some application of localization on surface.
Good morning. My name is Szymon Krupinski. So we work together with Francesco, and again, we are part of the old group from European Project Free Subnet. That was our beginning of our common work some 12 years ago, and yeah, we every now and then we still do some useful work together. So I'm going to present, let's say, tiny application of a subset of the technique that Francesco has discussed to surface robotics, and yeah, it's in our case it's interesting what can be done with this sort of relative navigation. So in many domains of robotics, in typical survey applications of underwater robotics, so AUVs doing area survey, area monitoring, the given wisdom is that you try to avoid obstacles, something that Francesco has already extensively described. You have to assure the security of your robot, but what we are pushing for is the contrary situation. So for us, the obstacles is just another source of information. The obstacles provide you this relative information about your environment that you can use to localize yourself. And I hope that this paradigm will become more and more, let's say, widespread in robotics. We won't be able to approach the environment. We will use it as a part of the navigation scheme. So okay, I'm about to talk about surface robotics, and you might want to ask the question: so why do we actually need anything extra for localization? Because we have GPS, right? GPS is a perfect source of localization, except some very strange conflict scenarios with GPS jamming. Nobody would ever need any other way of localization. But it's well, it's true, and I think in drone robotics or in surface robotics, in terrestrial robotics, everybody uses GPS, and the techniques built on top of that have, in the recent years, enabled many fantastic applications. GPS is cheap, the quality of localization is improving, and everybody uses this. But very often, especially for low-cost systems, GPS becomes the only source of localization, which might or might not have positive results. What we are going to show is that you might run into trouble with this technique. So let's put you a little bit in the context of what we have done. We have used a little surface robot, catamaran type robot about 2 meters long, which was equipped with a laser scanner, Velodyne 32 a laser scanner, and it was navigating on Charles River in Boston. So this is a very highly urbanized area. Charles River is surrounded by tall buildings. It's crossed by many bridges, and it's in the middle of the Boston area. So you can imagine what sort of environment it is. Why do we even touch this sort of setup? Why do we have an idea of working with this sort of scenario? Well, this can be developed into many useful applications. For example, many urbanized areas crossed by rivers are suffering from pollution, so plastic, let's say trash, floating down the rivers and reaching the ocean, and we all know how it ends up. There are often questions of how to survey some marine environments for let's say for the scenarios like spills or pollution. In many countries, let's say illegal dumping into rivers or runoff from agriculture is still a problem. And finally, cities like Paris are beginning to realize that next to the very saturated road system, a river can be used as a space for transportation of people, and they are experimenting with autonomous water taxis, for example. So this application of autonomous vehicles navigating on rivers is actually quite interesting. Right. So here, this is how it looks. That is upstream and downstream going towards Boston Harbor. And you can see that there is a lot of structures on the way of our robot. So what you see here is the orange path is the GPS track of the robot, and it all looks very good, right? You will agree with me that it seems that the localization problem has been solved. Well, it is only partially true, because in certain places, I hope you can read the labels in there. So where we have locks with very high walls or high structures or bridges, in fact, we have certain problems. So if I put it in slightly higher contrast, you can see that we have skips. We have places where GPS simply fails. Right, to be precise, this is where this sort of phenomena happens. We have broken line, we have very spurious position points which go far away from the actual path that the vehicle has followed. So the vehicle was constantly navigating more or less straight, and we see that the GPS sometimes indicates quite crazy position jumps. Right, so using this fantastic technique of localization as GPS, we might get problematic data. We can get holes in trajectory and false segments, mostly due to multipath. So I'm not an expert in GPS localization, but I would expect that the reflection from high walls and a loss of GPS signal followed by rapid acquisition can lead to simply wrong solution of the position. So. Right. This is the sort of scenario that our robot sees. It's simply we have a camera on the robot as well, and we are looking into means of using this camera for sensor fusion for better position estimation. But today I will talk to you about using point clouds coming from this sensor as a way to boost our localization precision. So it's a 360 degrees rotating head laser scanner from Velodyne. Yeah, you might say, okay, this guy is really restricting himself to surface robotics because this stuff cannot be used underwater. But okay, of course, that would be true 5 years ago or 10 years ago, but even in this conference, we have seen, let's say, better and better applications of laser positioning underwater, of laser sensors making their way slowly underwater. So, yeah, I actually apologize for not mentioning the producer of this brilliant laser that we have seen in our demo in my slides. So Velodyne is, let's say, on the low range of the performance in terms of precision, but it's a more accessible financially sensor, and it provides, let's say, a good alternative for mobile robotics, and for certain applications is a very popular choice. Right. So how to, one could say, okay, you guys can take simply whatever solution that exists for autonomous driving. Autonomous driving is rapidly, let's say, being adopted as a future of driving. Yeah, we could, well, of course, we get inspired by most of the techniques existing in autonomous driving, those that we know that are not patented or secret. But many factors, when you use a laser scanner on the water surface, actually prevent you from using directly some of the techniques in localization. So, first of all, many techniques for processing point clouds and matching point clouds or deriving information from point clouds, they rely on the presence of so-called ground plane. So whenever you are driving a car, you expect that the road in front of you or the ground around you is flat, and it represents a very good, let's say, point of reference in your point cloud. Another problem is that when, for example, this Velodyne sensor is very often used in applications where shown by Francesco, for example, navigating in a room, navigating in a corridor, navigating in a closed environment. But when we sail on water, we come from long distances. So not only our water surface that does not give a reflection, so we don't have this ground plane, which, let's say, makes part of the existing functions already ineffective for us, but also we are far away from most of the objects that give reflections. So we are far away from the edge, from the shores. We are hopefully far away from other participants of water traffic. We are far away from the bridge pillars. So this makes our point clouds relatively sparse and sometimes malconditioned compared to the ground point clouds. Finally, of course, we have phenomena like pitch and roll, which, well, when you drive an autonomous car, you probably don't expect much. Okay, so why GPS is failing us? Well, there are many reasons why GPS can fail us. So we have, most of all, we have the signal blocked by tall buildings, we have reflections, we have multipath, we have atmospheric distortion, and these things are improving, but we cannot hope that all of these trouble will be overcome. Okay, for those who work underwater, unfortunately, this will never happen underwater, but yes, GPS simply, despite improving parameters, is still sometimes problematic. And another problem that we have found is that there is no universal way of judging when your GPS is failing you. So, for example, the measure like horizontal dilution of precision is not always indicating that you currently have trouble localization. So in many cases, it will show you that you have, for example, a not very reliable arrangement of satellites, but in many cases related to our trials, we had good HDOP measure, which wasn't indicating that at this time we actually had big trouble localizing ourselves using GPS. Okay, so the idea of using point clouds to position ourselves is the same as scan matching outlined by Francesco, and it is well documented for using, for example, ultrasonic sensors or point clouds in terrestrial robotics. And what we want to do is to take consecutive measurements from our sensor and try to match one with the other in order to retrieve the position of how our own localization has changed in between consecutive measurements. And yeah, that gives very good results indoor, and it has been used in conjunction with sonar data in underwater settings. So we had SLAM running on this sort of information. So what we have done, we have used the PCL library to actually process our point clouds, and there exists a relatively well-developed, let's say, chain of processing for this sort of matching. So it starts with key point detections in these point clouds. Then we go to feature detection and descriptor computation. Then we combine them, try to find correspondences, measure our alignment, and reject correspondences if some of them are incorrect. And then with the best set of correspondences, we can finally estimate first the coarse alignment and then very fine alignment. So this is how things are usually done. Again, I have to put a word of caution in here. This usually works very well with dense point clouds at near distances from high quality scanners. In our case, we have not fulfilled many conditions for this working correctly, and but yet we were able to get some interesting results. Another, let's say, optimization that we wanted to introduce into our algorithm is that actually we are not changing the position in all directions. So when we sail on the river, we mostly displace our robot in X and Y direction. We are not, well, roll and pitch is something that statistically goes out of the picture because we stay more or less in the upright position all the time, and we only move in 2D, you can say. So we can reduce our point clouds in certain conditions to, let's say, flat projections of these point clouds on the ground plane. And this is another path that we have tested in order to reduce the complexity. Because if you can flatten your point cloud to an image, then first of all you can use some very well established image processing techniques to make matching, and to use matching to the information coming out of matching, as for example the yaw angle change or X and Y change to update your position, the robot's position. So the computational complexity is a very good advantage. So as you can see, when you flatten, as you cannot see because of the fine detail in this image, when you flatten 3D point clouds into images, you get pretty much what you would get from a sonar. That the images are eerily similar to sonar images, at least in the way we process them. So it's a technique that can be also applied to imaging sonar data. Right. So our results are far from complete yet. This investigation, despite simplicity, it has opened many questions, let's say, of how to do things better, and I can show you the results we have had so far. So we tried things first in a situation where we had good GPS localization, so we had good ground truth data, and you can see the vehicle going for docking. The orange line is the GPS positioning, and we have run our scan matching technique to recover the same information from the point clouds. And as you can see, we failed to position ourselves exactly, but the results are promising in the sense that you can see that when one looks at the dynamics of, for example, of yaw, we are recovering the right information. But we suffer from problems of drift. For example, when we compare consecutive measurements, gradually the errors between tiny errors between even very finely aligned point cloud data, they build up towards bigger errors. So we have to eventually use some fusion with other information in order to stay more precise. So if there was no GPS, we would have probably made an error of a couple of meters, but we detected the movement of our vehicle with respect to the environment. The problem is usually not actually the yaw detection, but the problem is the distance detection. Okay, so this is a scenario where our method is actually useful. So the blue track represents the GPS data that we get when we cross the bridge. So we go below the bridge with our vehicle. As you can see, well, the result is not very convincing. So first, whenever we get into the shadow of the bridge, the GPS information just goes crazy. So what we have done, we have continued processing the point clouds and scan matching between consecutive point clouds. Trying to figure out what's the good interval for it is yet another question we have to answer. And we have detected correctly. We have, let's say, obtained the result of detection of the crossing of, under the bridge correctly, which would have saved us in the situation where the GPS is not reliable anymore. So we can do this processing at about 10 Hertz, depending whether we use simplified methods or not. With simplified methods, we can go slightly beyond this figure, but there is still a lot to improve, and this is a very promising technique. And just a simple example of how positioning can be done with respect to the environment in marine applications. So there is definitely a lot of interesting steps still to be done. I will be very happy to discuss with you what your ideas are, and yeah, I think I will slowly stop here. Thank you very much. So we wanted to advertise a little special edition of a journal that we want all of you to contribute to, especially those who work with images, robotic perception, in adversarial environments, meaning where the data is not so easy to process.